Now these are basically easy problem. You see basically how you remember the reaction. You remember reaction by doing some problems, So you see in this case we have to do some problems. So they have a K2CO3 as a base. K2CO3 is something like NO2CO3. If you remember, NO2CO3 is a base same as K2CO3. So this will take H plus. So where you have H plus in these two compound, you have H plus here. So this will take H plus. If takes H plus, so you will have O minus. This is a product form, and once this is O minus is formed, this will act as a nucleophile. So this will act as a nucleophile, so it can attack on this carbon, and this Br can go. So if it pushes basically, so if you follow these steps, what you will have? You will have something like this. You will have OCH2 and then CH double bond CH2. So this is easy, and then you have to have OCH3 here. This will remain untouched. So this is an easy reaction, nucleophile attacking on alkyl halide. So this is basically alkyl halide. So this is a special alkyl halide, double bond. This is a allyl halide you can call. Now this is a O minus Na plus, same idea. This is will act as a nucleophile. Now we have to look at position or a side where it can attack. Of course there is a site here, and this Cl minus goes out. So if we follow this step, what you will have? You will have this and O and CH2, and then you have CHOH, and then you have CH2OH. Are you getting or not? Now this reaction, you see this HNO3H2SO4 is a well-known reagent, that is a nitrating reagent, but in this time this is not H2SO4. Of course this is a weak acid, acetic acid, but let us, okay, this reaction is a basically nitration, because I need a acid, even it's a weak acid. So it, okay, now I will have NO2 plus, nitration generate electrophile, E plus in this case is NO2 plus. So this will attack on the benzene ring. Now where it will attack, that is the only point. This is important in this problem. So this is CHO group. This is a basically deactivator. This is a activator, and this is again activator, if you remember. Now this group gives that ortho and para position. So this is the ortho for this, and this is para is already blocked. For this one, this is the ortho, and for this one, this is the para position. So these are the position, available position where it can attack. Now these are there is a class, basically there is a class where it should go, either it go at this position or these two positions. So I have to look for the which is more a stronger activator. So I have to look the stronger activator. For that I have made a chart here. Now if you see this chart, this is a NH2 is the strongest activator. So this is the strongest one, and then you have OH, then you have OR, and NO2 is a list activator. This is basically deactivator. NR3 plus is the this is the most deactivator. You can say a strongest deactivator. Important point we have in this problem, this OR, that is I can put R as a OCS3. OCS3 is less activator than OH. So OH is more activator. Are you getting or not? Sometimes it looks like OCS3, so somebody can think OCS3 is more activator because of the minus plus I effect, because this CS3 will show plus I effect. So it looks like OCS3 is more activator than OH, but that is not the actual case. So you have to remember this is the experimental fact. So you have to remember the experimental fact, no any choice we have. So even though it looks like that reasoning is not correct reasoning, OH I have to remember as the more a strong activator than OCS3. Now if I follow this thing, so I have OH here. So let us say OH is here. So OH will then this problem you have OH is here. So H will orient at this position. So I have to add NO2 at this position. So easy one. So I have to add NO2 at this position. So this is my CHO, and this is my OCS3, and this is my OH, and then I have to add NO2 here. And now let us make the ring a skeleton. Now the next problem, so easy one. I think all of you have got the idea. Now this problem, you see, this is something like heat, and let us say some H plus is also available. So what this H plus will do, in this case you have this oxygen, this H plus will go at this oxygen, it will form OH. So let us first form OH, and that is CH3 C double bond O and H, and then you have OH here. So you have OH, and now this is allylic carbocation gets generated. So you are generating a carbocation that is basically resonance stabilized. Of course, I have to flow the aura on this way. So this carbocation is a resonance stabilized. So you will have a positive charge here. So this is a allylic carbocation, and this is resonance stabilized. Now this carbocation, let us say for our purpose, I can take this charge. Now this carbocation where the charge is here. So you will attack on this OH. Now this phenol will orient either at this position. Phenol is more activated than NH group, so it will either NHCO-CH3, in this case of NHCO, this lone pair is slightly deactivated, resonance stabilized, so it will go at ortho position or para position compared to the OH, but para is already blocked, so it will go here. That is CH, I will have CH2CH, this is CH2CH, and then I will have double bond CH2. I think all of you are getting this one. So this is sometimes called a allylic rearrangement. So this is a allylic rearrangement. So this is a allylic rearrangement. Now next one, you see you have a activated ring and bromine. If you remember this reaction, whenever you have activated ring and bromine, as a multi-bromination or multi-halogenation takes place. So this is a case of multi-halogenation. Are you getting or not? So this, in this case, it will have multi-halogenation. So but the OH is, and this the OH will basically govern the orientation, because OH is more activated than OCH, CH2, CH3. We have already seen this one. Now OH, so this is the ortho position for OH. This is ortho is already blocked. This para is already blocked. So I have to add only one bromine because other positions are already blocked. Are you getting or not? So this we have to add one OH here, and then I have to add OET here, and then I have to add NO2 here, and now there is a bromine that is attached here. Now next problem, you see this is a slightly remembering kind of problem. You have to remember, no any clue. In this case, K2CrO3 Cr2SO1 can act as a oxidizing agent. So it will act as a oxidizing agent. What will happen? This alcohol, that is the OH, and this alcohol, both alcohol gets oxidized into ketone. So if I do this, if this alcohol gets oxidized into ketone, this also goes into ketone. Now there is a Cl. So now if I follow these steps, I have to write two double bond here. I cannot put double bond here, double bond here. I cannot put. So I can only option I have to put this. So this molecule is sometimes called quinone. So this is a quinone. Now this reaction is same reaction. This time I have a Lewis acid. AlCl3 is basically a Lewis acid. Idea is same as the S, that is the allylic rearrangement. You have to generate a carbocation again. So this OH, first there will be OH is formed. So you will have an OH. So this is a CH3, let me write Me, and there is a OH that is formed, and then you have CHMe and Me, and now there is a this carbocation that is basically a selenium ion is formed. Now this OH will govern orientation. It will go at ortho position or it can go at para position. Ortho position is slightly asterically hindered, so it can't go at ortho position. So I have only one option. It has to go at para position. So let us give this at para position. So if I attach C double bond, so that is a silyl group, that is OCH, C double bond OCH3. So this is sometimes also called Fries rearrangement. So Fries rearrangement. So this reaction has a name and it is called Fries rearrangement. It's easy one. It always oriented ortho or para position. In this case, para position is blocked. So I have only one option. Now this reaction, NaOH and dimethyl sulfoxide. NaOH is act as a base. Dimethyl sulfoxide is a solvent. So this is acting as a solvent. Now NaOH will take H plus and this minus. This is a nucleophile. Now I will have only one option. This attacks here and this goes. So this is a nucleophilic aromatic substitution. This substitution happens because this ring contains a deactivating NO2 group. So this is a deactivating group. So there is a deactivating NO2 group, and this basically nucleophilic substitution takes place. So I can write the product easily. So I have to follow these steps. So I have one OH, so this O, and now this O gets attached to this ring. So this side I have a ring, and this at para position I have a KNO2 group. And now let us make the double bonds, and now here I have one Me and here I have another Me. Now the next problem, so this says acetic acid. Again, this is the case of multi-halogenation. Now this OH, for this OH, this ortho position is already blocked. I have to give Cl here and I have to give one Cl here. So this is a case of again multi-halogenation. So multi-halogenation, if you remember, multi-halogenation happens if your ring contains activator group. So like OH say activator. So this is a activator. Are you getting or not? So this is a activator. In case of activators, ring goes to the multi-halogenation. So you have OH, you have Cl, and then you have Cl here also you have Cl. So this is a case of multi-chlorination, in this case you can call. Now this is a ester. So this molecule is a ester. This is a C double bond. If you see this carbon here, so this, if you look this side, so this is a ester group. Are you getting on? So this is a ester. There is a lone pair. This lone pair can attack on this carbon. This opens up and this goes. So this will form finally a amide plus alcohol. This is something like dissociation of a ester. So you will have CH3 here, and now this nitrogen is now get attached. One hydrogen I have to remove with attached with C double bond O, and this side I have a ring basically, so a 6-membered ring, and then this position just carbon, then I have to have OH, and this molecule is already gone, so that will form a phenol PHOH. So this is a PH OH. Are you getting on? So if you leave here, and then you have to remember this reaction also done in the slight acidic medium. So finally we'll have one phenol molecule. So you have a phenol molecule. Now the next one, this is a something called diazonium coupling. So this is a diazonium ion, diazonium chloride you can say. So this is a diazonium coupling reaction. So this is a diazonium coupling reaction. So this is a diazonium coupling reaction. Now what will happen? This ring is this OH group is a activator, and now this will act as a electrophile. So I have to attack this electrophile either at ortho position, para position is already blocked. So I have only one choice. I have to attach this group here. So let me attach this group here. So I will have OH, and then I have Cl. Here I have Cl. Here also I have Cl. So now I have to attach this group and double bond, triple bond. Basically no need to form a triple bond now. You can understand yourself. And now this is pH group. So this is a diazonium coupling reaction. Sometimes these compounds are basically used to form dye. So these compounds are basically colored compounds. So these are colored compound. So these are colored compound. Easy one.